I'm Sindhura, bearing roll number 611774. My topic is segmentation by morphological watersheds. The concept of watersheds is based on visualizing an image in three dimensions. This technique is often applied on its gradient image instead of working on an image itself. In this case, each object is distinguished from the background by its uplifted edges. There are three types of points. Point A, points belonging to a regional minimum. B, points at which a drop of water will certainly fall to a single minimum. C, points at which a drop of water will be equally likely to fall to more than one minimum. The set of points satisfying condition B is called the catchment basin or watershed of that minimum. The points satisfying condition C form crest lines on the topographic surface and are termed divide lines or watershed lines. This technique is to identify all the third type of points for segmentation. Basic steps. The figure A is the original view and figure B is the topographic view of the figure A. In order to prevent the rising of water from spilling out to the edges of the structure, we imagine the perimeter of the entire topography. This topography being enclosed by dams of height greater than the highest possible mountain. Suppose that a hole is punched in each regional minimum, shown as dark areas in figure B, and that the entire topography is flooded below by letting water rise through the holes at a uniform rate. Figure C shows the first stage of flooding, where the water shown in light grey has covered only areas that correspond to the very dark background in the image. In figure D and E, we see that the water now has risen into the first and second catchment basins respectively, and D is the second stage of flooding, and E is the result of further flooding. As the water continues to rise, it will eventually overflow from one catchment basin into another. The first indication of this is shown in figure F. The F is the beginning of merging of water from two catchment basins. A short dam was built between them. Here, water from the left basin actually overflowed into the basin on the right, and a short dam consisting of single pixels was built to prevent water from merging at the level of flooding. The effect is more pronounced as water continues to rise as shown in figure G. The figure G are the longer dams. This figure shows a longer dam between the two catchment basins and another dam in the top part of the right basin. The latter dam was built to prevent merging of water from that basin with water from areas corresponding to the background. This process is continued until the maximum level of flooding is reached. The final dams correspond to the watershed lines, which are the desired segmentation result. The result is shown in figure H as a dark 1 pixel thick path superimposed on the original image. The figure H is the final watershed segmentation lines. The watershed lines form a connected path, thus giving continuous boundaries between regions. One of the principal applications of watershed segmentation is in the extraction of nearly uniform objects from the background. Regions characterized by small variations in grade levels have small gradient values. Thus, in practice, we often see watershed segmentation applied to the gradient of an image rather than to the image itself. Dam construction. It is based on binary morphological dilation. At each step of the algorithm, the binary image is obtained in the following manner. Initially, the set of pixels with minimum gray level are 1, others 0. In each subsequent step, we flood the 3D topography from below and the pixels covered by the rising water are 1s and 0s. Notations 1. M1, M2. These are set of coordinates of points in the two regional minimum. C suffix n-1 of M1, C n-1 of M2. These are set of coordinates of points in each catchment basins associated with M1, M2 at stage n-1 of flooding. And C n of n-1. This is union of C n-1 of M1, C n-1 of M2. At flooding step n-1, there are two connected components. At flooding step n, there is only one connected component. This indicates that the water between the two catchment basins has merged at flooding step n. Use Q to denote the single connected path. Steps are repeatedly dilate Cn-1 M1, Cn-1 M2 by the 3 by 3 structuring element shown, subject to the following condition. Constraint to Q, center of the structuring element cannot go beyond Q during dilation. Figure A is the two partially flooded catchment basins at stage n-1, and figure B is the flooding at stage n, showing that water has spilled between basins. For clarity, water is shown in white rather than black. Figure A shows portions of two catchment basins at flooding step n-1. Figure B shows the result at the next flooding step n. The water has spilled from one basin to the other, and therefore a dam must be built to keep this from happening. The origin is the structuring element used for dilation. Figure D shows that the first dilation pass in light gray expanded the boundary of each original connected component, and D is the result of dilation and dam construction. The dam is constructed by the points on which the dilation would cause the sets being dilated to merge. Setting the gray level at each point in the resultant path to a value greater than the maximum gray value of the image, usually max plus 1. Watershed transform. Denote M1, M2 and so on MR as the sets of coordinates of points in the regional minimum of an gradient image G of x, y. Denote C of Mi as the coordinates of the points in the catchment basin associated with regional minimum Mi. Denote the minimum and maximum gray levels of G of x, y as minimum and maximum. Denote T of n as a set of coordinates s, t for which G of s, t less than n. Flood the topography in integer flood increments from n equal to m minimum plus 1 to n equal to maximum plus 1. At each flooding, the topography is viewed as a binary image. Denote Cn M1 as a set of coordinates of points in the catchment basin associated with minimum Mi at flooding stage n. Cn of Mi equal to intersection of C of Mi with that of T of n. Cn of Mi equal to T of n. Denote C of n as the union of the flooded catchment basin portions at stage n. Initializing. Let C of minimum plus 1 equal to T of minimum plus 1. At each step n, assume C of n minus 1 has been constructed. The goal is to obtain C of n from C n minus 1. Denote Q of n as the set of connected components in T of n. For each Q belongs to Q of n, there are three possibilities. Intersection of Q with that of C n minus 1 is empty Q1. A new minimum is encountered. Q is incorporated into C n minus 1 to form Cn. Intersection of Q with that of C n minus 1 contains one connected component of C n minus 1 Q2. Q is incorporated into C of n minus 1 to form C of n. Intersection of Q with that of C of n minus 1 contain more than one connected components of C of n minus 1 Q3. A ridge separating two or more catchment basins has been encountered. A dam has to be built within Q to prevent overflow between the catchment basins. Repeat the procedure until n equal to max plus 1. Watershed transform of binary image example. A is the original image and B is the negative of image A, and C is the distance transform of B, and D is the watershed transform of C. Distance transform of a binary image is defined by the distance from every pixel to the nearest non-zero valued pixel. Example 2. A is the original image, B is the gradient image of image A, C is the watershed lines obtained from image B. Each connected region contains one local minimum in the corresponding gradient image. D is the watershed lines obtained from smoothed image B. The use of markers. Internal markers and external markers. These internal markers are used to limit the number of regions by specifying the objects of interest. like seeds in region growing method, and can be assigned manually or automatically. And regions without markers are allowed to be merged. External markers are those pixels we are confident to belong to the background. Watershed lines are typical external markers and they belong the same region. Watershed based segmentation. Use internal markers to obtain watershed lines of the gradient of the image to be segmented. Use the obtained watershed lines as external markers. Each region defined by the external markers contains a single internal marker and part of the background. The problem is to reduce to partitioning each region into two parts. One object containing internal markers and a single background containing external markers. Global thresholding, region growing, region splitting, and merging or watershed transform. The image A is showing internal markers, those are light gray regions, and external markers, those are watershed lines. And B is the result of segmentation. Note the improvement. Thank you.